Morning all, and today we have a very interesting matrix problem. As you can see, the first one is already asked in J advance in a little altered fashion, and the idea was which of the following matrix M with real entries are possible such that M square is something. So of course in that problem you need to calculate just data of M, and if it is positive it's going to help, right? So we can't have any matrix M with real entries such that M square is going to be 0, 1 and 1, 0. We can't have any matrix M with real entries such that M square is going to be this. Why? Because if it is the case, then data of M square will be data of that matrix, and this is -1, which is not possible. So this was the very basic question of the advanced. Let's try a little bit more advanced version of this problem. And very surprisingly, what we are going to see is this can be solved using other department of mathematics. So let me pose the question. You have to find all real matrix M with 2 cross 2, so that is square is going to be this. And question 2, repeat the same for all real matrix M with entries real number with dimensions 2 by 2, so that M to the power 5 is going to be 1, 1, minus 1. So as usual, you can give a check for the first one. Like it's definitely possible to have matrix because data of M square is going to be 1. So data of M is plus minus 1. Similarly, for the second problem, data of M to the power 5, anyway, it doesn't matter. So it's 2, so data of M can be 2 raised to power 1 by 5, right? Now, can we solve this problem using complex number? And that feels such a decent idea of solving this, because the first time when I looked at a problem, immediately I got a thinking like this 0, 1, minus 1, 0 looks very familiar to us. So let's try to investigate solving this problem using some other cool method. Of course, one of the way of doing this is you can take a matrix xy and maybe zw. You multiply it with xy, zw, get 4 equations for unknown, and then solve them. And with those 4 equations and 4 unknown, we'll get the real values of xy, zw, and that will give the possibilities for number of matrices. In the same way, you can solve even M to the power 5, which will be drastically traumatic experience because we have to multiply M with 5 times and then 5 equation will be okay. In the same way we can do for M to the power 5, where I'll take again xy zw and we'll multiply 5 times. Finally at the end we are going to get 4 equation and 4 unknown, and again we'll solve. The reason you can't do it just with the data of matrix, because if data of matrix, if I'll take on both sides, we are going to get it 1. So data of M will be plus minus. Now this is necessary condition but not sufficient, because we don't know whether data of M square is coming from this matrix or something else, right? Because even other matrix might also give data as 1. For example, suppose if matrix were 0, 1 by 2, minus 2 and 0, still its determinant is going to be 0 plus 1, which is 1, right? So we don't know the source. So if just with determinant evaluation and taking data on both sides, you can't find the perfect number of matrices for xyzw, although that's necessary but not sufficient condition. Okay, now you can clearly see for the first matrix, though the basic approach of xyzw might seems okay because it's not that traumatic experience, but the second, writing 5 powers and then solving for those 4 equations in higher degrees will be definitely a bad way of doing this. So is there a smart way? The answer is of course yes. And here we go with the completely new line of thinking. So before we go further, it's better to analyze what does 0, minus 1 and 1 comma 0 pictorially or graphically represent. As you know, like this works as an operator. So every matrix can be used as an operator. And to get a feel of that, we can operate this on a vector x comma y. What I mean is, we take a point x comma y and see how x comma y changes, okay, in terms of its orientation or length or scaling or descaling when it is operated by this matrix. Okay, so let's call this matrix A. So let's see what is the behavior of xy when reacted with A. So clearly we'll get the final answer as y, and we have minus x. Now can you geometrically tell where y and minus x is? Not so bad. So we have this x distance and this y distance. Now the x coordinate is gonna be y, and the y coordinate is gonna be x. So what I mean, if I take 1 comma 2, it will go to 2 comma minus 1. Okay, I can take minus common and it will become minus y comma x. Now there's something easy to visualize, because where will be minus 1 y comma x? Let's say somewhere this point is. Now clearly you can see the slope of this line is y by x, and the slope of this line is minus x by y. So the product of slope is going to be minus 1. m1, m2 is minus 1. And that's a surprising result. So what we got is minus y comma x will be exactly opposite to this, right? It is something like this. So this vector is y comma minus x, and we have minus y comma x. So it feels like x comma y is rotated by a 90-degree angle in anti-clockwise sense, and then it's reflected. Now this is something special which has link with complex number, because you know, in complex number the work which is done exactly equivalently to rotate a number is basically, so this can be achieved by a complex number, because we know from this theory of complex number, if you have got a point x plus iy in the organ plane, and if you multiply this with I, the resultant point will go to xi minus y, which is minus y plus xi. And that's so surprising. It means basically multiplication with root minus 1, which is I, rotates the complex number, or rotates the vector by 90-degree in anti-clockwise sense. And that's a clue between this matrix problem and this complex number. So here we go. As we know, like x comma y is rotated to minus y comma x. So this matrix, the operation 0, 1, minus 1 comma 0, feels like if something reacts with that, that will give minus times of minus y comma x. Now we know the given expression can be equivalently represented if on a complex plane x comma y I represent as x plus iy, and we know the answer that we are getting is minus y plus xi times minus times of that. So answer is minus y plus ix. So to go from here to here, we must multiply with the complex number minus I. So now the takeaway is 0, 1, minus 1, 0 is behaving like negative iota. So I can give an equivalent definition. Let's call me Kunal's definition, or whatever with my name. Since I'm not so celebrated, so it's better not to take my name. Okay. Anyway, so we can give a new name to this. So minus I can be represented as a rotation matrix as well, which is 0, 1, minus 0. And again, you can multiply with minus 1 on both sides, and we can equivalently represent I as 0, minus 1, 1 and 0. So this is our newly created definition of iota. You might give a try to calculate I square, because I square is 0, minus 1, 1, 0, 0, minus 1, 1, 0. And let's say what we're getting. So we have 0. So let's give a try for multiplication. Let's see what we're getting. So we have minus 1, 0, 0 and minus 1. And that's so surprising, because minus 1 times just identity matrix. Okay. And equivalently, if I represent I with the rotation matrix, identity matrix is represented by, so basically 1 is represented by, in this new world, 1, 0, 0, I. So that is the equivalent rotation, because what is the significance of 1? When you multiply any number with 1, it will retain its identity. What is the significance of 1? Because when you multiply a number with 1, it will retain its identity. So that's exactly happening with multiplying 5 with any identity matrix, which is basically 5, 0, 0, 5. So pictorially, if I take a number 1 as an operator, and if I multiply this with 5, it will remain there. So this is input, and that will become output. So input and output is same. So I can treat 1 as if it were an identity matrix. I'm treating I as if it is a rotation matrix. And with that, I can now represent any matrix in the form of iota. So any matrix x plus iy can be equivalently represented with x times 1 plus I times 1. Now what is x times 1? 1 is behaving like an identity matrix 1 0 0 1 plus, according to our newly created definition of iota, 0 minus 1 1 0 0 minus 1 1 0. We can give x plus iy is equivalent to the notation. Now x is behaving like a scalar here, and this is a matrix operator, so that x 0 0 x, and now you have y minus y, so 0 minus y. Okay, so with this notation where x and y is just number, real number, so we get our answer as x minus y, y and x, and that's something really magical. Okay, you see how nicely I'm able to represent any number in the coordinate system using a matrix. So this is our new mathematical discovery. Now let's come back to our problem and let's evaluate ms square equals 0 1 minus 1i. So that's what I've written here. According to our representation, 0 minus 1 1 0 is represented at I. So minus of this will be minus I. Now I can write using de Moivre's theorem, or in Euler's representation, I can be written as e to the power I pi by 2 plus 2k pi. So m is equivalent t ka power minus I pi by 4 plus k pi. Now of course k can take multiple values, so you can take k equal 0, 1, 2, 3, 4, 5, 6 and so on and so forth. Even you could have started from minus 10, minus 9 and so on. Now this value will keep on repeating, so it will be cyclic. So if I'll put k equals 0, I'm getting value of n in terms of complex notation, which is 1 by root 2 minus 1 by root 2. If I take other value of k as 1, I'm getting minus 1 by root 2 plus I by root 2. If I take, let's say, value 2, we'll get back to this result. Again, 3 will give back to. So you'll keep on oscillating within this. So this will give repeated solution. Hence, to get the distinct solutions of this matrix, we have got just two distinct representation in complex form. And now let's to decode it. So we'll put this back to our matrix world. And what does the first equation decode to? So now clearly we can see the first equation. If we'll move backwards, so x plus iy denotes x and minus I. So here it will become 1 by root 2. And that's, guys, minus 1 by root 2 comma 1 by root 2. So this is one of the solutions for our matrix. The other solution, if we decode it back to our world, is going to be minus 1 by root 2, minus 1 by root 2, and this is 1 by root 2 minus 1 by root 2. So let's try to check whether this is indeed a solution. So verification, let's take 1 by root 2, 1 by root 2, minus 1 by root 2, 1 by root 2, and multiply with 1 by root 2, 1 by root 2. Okay, so when we multiply, of course, we'll get first into this. So that's going to be 0. The second thing is going to be 1. And you have the third one, which is going to be minus 1. And the fourth one is 0. So we have 0, 1, minus 1, 0. And you see that's exactly the solution for our equation. So we have indeed extracted the matrix answer using a very beautiful technique of identifying with complex number. Let's try the second solution. So minus 1 by root 2, minus 1 by root 2. And then we have 1 by root 2 and minus 1 by root 2. Let's multiply this with the same matrix. And what you get is a surprising result. So now again, this into this, that guys simply dies. The second one gives you 1. The third one gives you minus 1, and the fourth one is dead. And wow, that's such a crazy result. Now, of course, as a mathematician, it will be thrilled to generalize the result, not only to the, here second root of iota we have done. We can even generalize for m5 equals this. Okay, so you can then yourself give a try. You try to represent it in terms of x plus iy according to the newly discovered mathematics which I have done. And then express x and y in polar format. Once you know polar format, you solve the corresponding z5 equals that are e to the power I theta equations. We'll have 5 distinct roots. Move it back to your matrix world and decode the question. Hence, we are solving matrix question with complex numbers. And just to bid a bye-bye to this concept, we can give even this problem m5 equals, let's say, I give you 1. So we have 1, 0, 0, 1. So this is equivalent to telling z5 equals 1 in the complex world. And you know it's answerally fifth root of unity. So z is going to be 1, alpha, alpha square, alpha cube, and alpha 4, such that all the solutions lies on this complex plane. Okay, so all these solutions lies on this complex plane. And all these point is definitely the valid solution of this. Let's give a try. One of the solution is definitely z equals 1, which represents identity matrix. So one solution is m is I, which is of course true. The other solutions will be in polar format. It's gonna be cos 2 pi, as you know total angle is 2 pi, and it will be divided by fifth root of unity into 1/5 part. So cos 2 pi by 5 plus I sine 2 pi by 5. So this is another solution. So let's decode this, how that solution will look in matrix format. It will look as cos 2 pi by 5 minus cos. So let's decode it and let's see how it looks in matrix form. Cos 2 pi by 5, yeah, minus sine 2 pi by 5, and we have sine 2 pi by 5, and cos 2 pi by 5. And let's see what does it mean. So let's take the 5 power. So if we take the 5th power of this, very surprisingly what you're gonna see is this will give you just iota 1001. Okay, in fact 5th power will directly give you cos 2 pi, and that you can do by simply multiplication or using by rotation theorem, because this matrix is fundamentally rotating any vector with an angle of 2 pi by 5. So 5 times if you rotate, you will be back to home, to the place 1, 0, right? That is a geometrical explanation. Or using De Moivre's theorem, it will be, once you multiply it 5 times, if you want, you can do it. You'll just get this. That evaluates to 1, 0, 0, 1. So the beauty of the questions is clearly remarkable, and it also tells you, like in general, you can solve for even m to the power 2023 equals iota. And even like this will involve answers like cos 2 pi by 2023 and minus sine 2 pi by 2023. One of the solution, I mean, usually which surprises you. Because you see clearly from this matrix, such a neat and clean equation is giving birth to this cos and sine. So matrix is connected with complex number, and complex number connected with matrix, and complex number has a real connection, and matrix contains real entries. All these are connected in a way to each other, and this is the beauty of mathematical thinking, where you don't read maths in compartment, but it's a seamless connection between different ideas.